Hi, I'm Bob. Welcome to the Stata course on regression analysis and estimation methods. In today's topic, we will examine how to run the ordinary least squares OLS regressions using Stata. OLS is the most commonly used linear regression method. We will use Stata's regress command to run the OLS regression models. We use the course dataset BOB.dta. Please download it from the link below. The dataset contains information on the U.S. workers between 25 and 54 years old who participated in the panel study of income dynamics PSID surveys. We have already used this dataset in our summary statistics and data management course. It is a good idea to review that course before learning regression and estimation with Stata. Let's open the dataset and describe it. We find the hourly wage variable, hwage. Suppose we are interested in the relationship between the hourly wage and several other variables in the dataset, such as educational attainments, marital status, and age. Could they explain the workers' earnings? Let's run a linear regression with the hourly wage as the dependent variable and schooling, married, and age as the independent variables. The dependent variable is also called the outcome variable. The independent variable is also called the explanatory variable in economics. We code in a do file. We use the regress command for OLS regression models. We type regress hwage followed by schooling, married, age. Let's execute the command. In the results window, we see the output of OLS regression. There are two parts of the output. The upper part contains the model statistics, and the lower part contains the estimated coefficients. Let's focus on the lower part today. We see that the outcome variable is the hourly wage, hwage. There are three explanatory variables: schooling, married, and age. And there is a constant term. Then we see the estimated coefficient for each explanatory variable. The columns give information about the estimated coefficients, the standard errors, the t-statistics, the p-values, and the confidence intervals. Usually, we write down the estimated equation in the following form based on the Stata output. Y hat presents the fit value or the predicted value of the outcome variable. Beta hats are the estimated coefficients for the explanatory variables. In this case, the estimated equation is as follows. We often write down the standard errors below the coefficients. The coefficient of the constant term is the predicted value of hourly wage when all the explanatory variables are set to 0. It is not likely to happen, so it is not of interest in applied economics. Let's interpret the slow coefficients. The estimated coefficient for schooling is 2.68. It implies that the hourly wage increases by $2.68 on average for one more year of schooling completed, holding other factors fixed. The estimated coefficient for married is 3.36, meaning that Married workers earn $3.36 more per hour on average than unmarried workers, other things equal. The coefficient for age is 0.28. It suggests that the hourly wage increases by $0.28 as age increases by 1 year, holding other variables constant. Before running the regression, we often use the summarize command to find the information of the variables, such as their meanings and units. It helps us have an accurate interpretation of the estimates. The t-statistics and the p-values tells us whether the coefficients are significantly different from 0. The t-statistic is computed as the ratio of the estimate to its standard error. The null hypothesis is that the coefficient is 0, while the two-sided alternative hypothesis is that it is not 0. The p-value is the smallest significant level at which the null hypothesis would be rejected. So a large absolute value of the t-statistic or small p-value indicates a statistically significant coefficient. In our model, all estimates are statistically significantly different from 0 at the 0.1% level. Therefore, all explanatory variables in the model can explain the worker's hourly wage. The variables schooling and age are continuous variables in the model. The variable married is a dummy variable with two values, 1 and 0. In Stata, we can use the prefix i. in the front of the dummy variables or categorical variables. We can also specify the base levels option so that the base group would be included in the output. It tells us which one is the base level. Alternatively, we can set the set base levels on before running regressions. By doing so, we do not need to use the base levels option for each regression. We have another categorical variable, health, in the dataset. It has 5 categories: excellent, very good, good, fair, and poor. Using the i. prefix, we can estimate the coefficients for each category. The excellent is the base category or base group. The very good workers earn $1.4 less per hour than the excellent workers. The good health group earns $3.8 less. The fair group earns $5.6 less, and the poor group earns $7.2 less compared to the excellent group. By default, Stata will take the first category as the base group. All results should be interpreted relative to the base group. We can change the base group by using the ib. prefix. We specify ib5. in front of the health variable. Now, the poor health workers become the base group. Notice that using the i. prefix in front of a categorical variable is equivalent to using several dummy variables in the model. Using the method we have learned previously, we can generate 5 dummy variables from the categorical variable health. We include 4 of them in the model to avoid the dummy variable trap. And we find the same results as using the i. prefix in front of the categorical variable. Today, we have discussed the regress command in Stata for OLS regression. We learned to interpret the estimated coefficients for continuous variables and categorical variables. See you tomorrow on the next topic. It is Lunar New Year's Eve now. I wish you a happy, lucky, healthy, and prosperous year of the dragon. Take care.